this, and given this, and given this, we can make some interesting deductions. So now we start doing a kind of numerical analysis. So what I'm going to do now, and this may surprise you, I'm going to prove that R, the remainder, is of this form. Surprised? So I will now show that that's the case. So this remainder, this residue, is of this form. So let's prove that. And you may say, well, so what? Well, it's just another step in the proof, right? But if I can show that R, by plugging in this value of H here, I can show that R is of this form. So in other words, R belongs to this set. Maybe you're starting to get a bit of a hint where this proof's going. As usual, I need space. Okay. All right. So let's prove that this remainder here, using the division algorithm, let's prove that this R is of this form. So in other words, this integer here, R, belongs to the set S because it has this form. A times some integer plus B times some integer. It has that form. So let's actually prove it. So now, okay, take this and rewrite it. So, oh god, it's not dry. This problem is driving me crazy. So how to solve it? Is it possible to get marker pens that wipe off easily? I mean, am I the victim of cheap Chinese products because I'm living in China? Because this doesn't work. Well, I'll try this time. Okay, so rewrite R. So just take QHO the other side. So you'll get R equals A minus QH, A minus QH. Okay, from here. And now H you've got here, so that's A minus Q. Now plug this in, so it'll be A x naught plus B y naught. Okay, now rearrange those terms and you'll get something like this. 1 minus qx naught qx naught A, okay, plus, you can see why I need the book, right? No way I'm going to remember all this. Minus qy naught B, right? So this is just rearranged in terms a bit. But look, this is just an integer, right? Some integer A, so like it's of this form, some integer A, and this also is just an integer B, so some integer B. So from this, that implies that R belongs to S. Okay, because R is of that form. It's of that form. Look, see, integer A plus integer B. That's of that form. Therefore, this remainder, this residue, this R here, belongs to S. Okay. All right. Now the next vital step. Now, from the division algorithm, you've got this, right? That remainder there has to be less than H, right? So R is greater or equal to 0 and less than H. Okay? So now R is less than H. Now R is an integer. Okay? R is an integer. That comes from the division algorithm. But H, remember how we defined H? H is the smallest positive member of S. But look, we've got R is smaller than H. Got a problem there, right? By definition, we defined H to be the smallest positive member of this set. And R is less than H by the division algorithm, just here. So how can you reconcile, how can these two be brought into agreement so they don't conflict with each other? So if R is not 0, it's positive. Well, yeah, R is greater or equal to 0. So if it's not 0, it has to be positive, right? And it's less than H, strictly less than H. But H, we're told, is the smallest positive member. But if R is non-zero, so it's positive, that means that R is smaller than H. But that contradicts what we've said here. So the only way this and this can become compatible is that R equals 0. Now 0 is not positive, right? So if R is 0, it's not positive. So this does not conflict with that. Okay? So the only way to make that and that compatible is to say, so that implies that R is 0. Okay? Hope you followed all that reasoning. Not trivial. Okay, so R is 0. Now if R is 0, A equals QH. So that implies, if R is 0 here, so A equals QH. A equals QH. And that implies that H divides A. Right? You can divide A by H. H divides into A. So H divs, D-I-V-S, in other words, divides, H divides A. Alright? Okay, next step, you can go through the same kind of analysis with B. So instead of, you can split, instead of having an A here, you put B. And you'll have not a Q, let's say a little P or something. So you can go through just the same analysis, the same kind of trick, and you end up with proving that H divides, it's just the same analysis, trust me, or do it yourself, just prove it yourself. So H divides B. Okay? You see, you're starting to see where this is going now, all right? So if H divides A and H divides B, that implies H is a common factor, right? H is a common factor. Common factor of A and B, right? H divides A, H divides B, therefore H is a common factor. But, well, I've rubbed it out, but we started, we were trying to prove if P then Q, and what is P? P says that A and B have no common factor. They are relatively prime. Okay? Now, if A and B are relatively prime, the only common factor that they have is 1. Right? Now, H is a common factor. But A and B have only one common factor, and it's 1. So H must be that common factor, that single common factor, right? Therefore, H is 1. H is 1. So this is 1. Okay. So we have 1 is AX 0 plus BY 0. So therefore, these integers, there are two integers x naught and y naught, such that the AX plus BY is 1. So we've proved it. Whew. That non-trivial. Okay. Right. Now that's probably the hardest proof of the lecture, and for all I know, may even be the hardest of the course, the whole lecture set. Now, it's very important because we can now use this proof, theorem 1, for other proofs. So let's do now some other proofs, and I'll stop here for the moment.